Our past is filled with silent questions carved in stone and metal. The most incredible structures from ancient times are not just old, they are actively confusing. Modern researchers with advanced tools and deep knowledge still stare at these achievements and cannot fully explain how they were built, or sometimes even why. This is not a tour of ruins. This is an investigation into 40 specific engineering puzzles that defy straightforward answers. By the end, you will see human history not as a simple timeline, but as a landscape dotted with brilliant, mysterious peaks. How did a civilization move an 800-ton block of stone, or build a computer 1,000 years ahead of its time? These enigmas force us to reconsider everything we think we know about the limits of early innovation. They whisper of forgotten techniques and lost schools of thought. What does it mean when the work of our ancestors still outsmarts us today? These mysteries often begin with the most famous example, yet its familiarity has dulled our sense of wonder. The Great Pyramid of Giza is not merely large, it is unnervingly perfect. Modern surveys reveal a foundation covering 13 acres that is leveled to within less than an inch. That is like laying a perfectly flat floor across an area the size of several football fields, using only bronze tools, ropes, and human sight. The sides of the pyramid are aligned to the cardinal points with a deviation so slight it seems impossible, a feat of astronomy and geometry combined. Each massive limestone block was cut with joints so precise a credit card cannot slide between them. This was not brute force construction, it was engineering of a surgical caliber. Researchers have attempted to recreate the techniques using the tools archaeologists believe were available, only to find the margin for error is virtually non-existent. How did an ancient workforce without lasers or modern measuring devices achieve and maintain such flawless accuracy across decades of construction? The precision itself is a silent argument for a level of technical knowledge we have not yet credited to that era. It suggests a master plan executed with unwavering discipline, a secret now buried not in the pyramid's chambers, but in its very angles and seams. That flawless precision only deepens the central logistical puzzle. How do you move 2.3 million stone blocks, some heavier than a military tank, across miles of desert, and then lift them hundreds of feet into the air? The quarries for the fine white limestone were across the Nile. The granite for the interior chambers came from over 500 miles to the south. Each of those granite blocks weighs between 50 and 80 tons. The leading theory for transport involves wooden sledges gliding over wet sand, which a clever physics experiment has shown significantly reduces friction. But this still requires an immense flat roadbed and an army of laborers pulling in unison, a coordination nightmare over such vast distances. Once at the site, the challenge of lifting begins. The classic external ramp theory falters when you calculate the ramp's own colossal size, requiring as much material as the pyramid itself. The more elegant internal ramp idea, where a corkscrew tunnel ran inside the growing structure, is compelling but lacks any physical evidence within the pyramid. Others propose a system of levers and counterweights, a kind of monumental seesaw, yet this becomes wildly complex for the highest tiers. The truth is, no single model we have devised explains the entire process with the efficiency the ancient builders clearly possessed. Their method seems to have been a hybrid, a lost orchestration of simple machines and profound logistical genius that we can only glimpse in fragments. This same stone-moving enigma appears even more starkly in a place where the blocks are not just heavy but unimaginably so. Yet in Lebanon, a Roman-era site presents a stone so large it redefines the concept of heavy. The platform at Baalbek, known as the Trilithon, holds 3 limestone blocks, each estimated to weigh around 800 tons. That is the equivalent of 200 full-grown elephants, or 3 fully loaded jumbo jets. These stones were quarried over a kilometer away, dragged to the site, and then hoisted over 20 feet into the air to sit in a wall with joints so tight they challenged perception. Roman engineering was brilliant, famous for aqueducts and roads, but even their most ambitious projects typically involved stones a fraction of this size. The known cranes and pulleys of the Roman world would have struggled immensely with such a load. The puzzle deepens in the nearby quarry, where an even larger monolith lies partially cut, a silent titan known as the Stone of the Pregnant Woman. It weighs an almost incomprehensible 1,000 tons. Its very existence asks a haunting question. If this was the next block intended for the temple, what method did they plan to use that could move a mountain? The abandoned stone suggests a limit was reached, either of engineering or of will, leaving us with only the evidence of what they did achieve. This forces a humbling realization. At Baalbek, we are not looking at a typical Roman construction. We are witnessing an outlier, an event that pushed their documented capabilities to an absolute extreme, or perhaps borrowed from a much older, forgotten tradition of megalithic construction. Here, the mystery is one of pure scale and force. But what happens when the ancient puzzle shifts from moving gigantic stones to fitting smaller ones with impossible, laser-like precision? The same obsession with perfect seams appears halfway across the world, on a windswept hill overlooking the ancient Inca capital. The fortress of Sacsayhuamán is guarded by walls that seem to defy logic. They are built from colossal limestone blocks, some weighing over 100 tons, each one a unique, irregular polygon with as many as 12 sides. Yet these giant puzzle pieces lock together so perfectly that the joints between them have no gap. For centuries, people have said you cannot slide a piece of paper or even a razor blade between the stones. This was achieved entirely without mortar. The engineering puzzle is not just about moving the stones, but about the insane precision of the cutting and fitting process. How do you custom shape a 100-ton block to fit seamlessly against 2 or 3 other uniquely shaped neighbors? The conventional explanation involves pounding stones with harder rocks to slowly shape them, then grinding the surfaces with sand. But when researchers try to replicate this, the margin for error is microscopic. One wrong strike could ruin an entire block, wasting months of labor. Some theories suggest the Incas used a method of heating the stone with fire and then rapidly cooling it with water to make it easier to work, or that they employed some form of precise measurement and template system that has been lost. The truth is, every theory remains speculative. The how remains locked within the stones themselves. This was not merely for show. This zigzagging, interlocking design gave the walls an incredible secret strength. Peru is a land of intense seismic activity, of earthquakes that topple modern buildings. Yet these walls, built over 500 years ago, have withstood every major quake. The polygonal masonry allows the entire structure to flex and settle during tremors, the stones rocking and settling back into place rather than cracking apart. This reveals a sophisticated, almost intuitive understanding of seismic engineering that conventional history books rarely grant to the Incas. They were not just stacking rocks, they were designing a living, flexible shield against the power of the earth itself. That concept of stones moving as a unified, resilient whole finds a strange and even more precise echo in another part of the world, where the fitting is so exact it seems to deny the passage of time itself. But the seamless stonework of Sacsayhuamán is not the final word on this mystery. In the humid Florida landscape of the early 20th century, a single man performed a feat that feels pulled from ancient legend. Edward Leedskalnin, a slight Latvian immigrant weighing barely 100 pounds, spent 28 years single-handedly building what he called Coral Castle. From the 1920s to the 1950s, he quarried, shaped, and positioned over 1,000 tons of colossal coral rock. He worked almost entirely alone, often at night by lantern light, shrouding his methods in secrecy. When asked how he managed it, he would only offer a cryptic smile and say he understood the laws of weight and leverage used by the builders of the pyramids. The results are bewildering. There is a 9-ton stone gate perfectly balanced on a simple truck bearing, so exquisitely engineered that a child can push it open with a single finger. It rotated flawlessly for decades until the mechanism was finally repaired in the 1980s. There is a 23-ton obelisk, a 22-ton crescent moon block, and numerous multi-ton rocking chairs carved from solid stone. The precision is everywhere. He cut and fitted massive blocks with joints as tight as any Inca wall, and even carved a functional sundial accurate to within 2 minutes. The central enigma is simple. How did one man with no visible machinery, no large teams, and only rudimentary tools documented in old photographs accomplish this? He claimed to have rediscovered the building secrets of the ancients, a knowledge of magnetism and cosmic force. Skeptics propose he used simple block and tackle systems, tripods, and clever leverage. But when engineers have tried to recreate his work using only the tools he was known to have, they find the task nearly impossible within the time frame and with his limited physical strength. Coral Castle stands as a modern monument to a persistent ancient puzzle. It suggests that the gap between official history and achievable reality might be bridged by forgotten principles that one man perhaps briefly reclaimed. This mystery of manipulated stone finds a parallel in a different kind of manipulation, one that involves not rock but metal, and a question of how ancient people achieved what our modern science says should have been impossible for them to create. While Edward Leedskalnin was shaping coral in Florida, a far older metal object in India was defying a more fundamental law of nature. The Delhi iron pillar has stood quietly in a courtyard for over 1,600 years. It is a single, solid shaft of wrought iron, over 7 meters tall and weighing more than 6 tons. Forged in the 4th century, it has endured monsoon rains, blistering heat, and the pollution of a modern metropolis. Yet it shows almost no sign of the rust that should have consumed it centuries ago. This is not a coating or a paint. The pillar itself, its very material, resists corrosion. For a long time, this was considered a miracle or a testament to superior ancient metallurgy. Modern science, however, has peered into its atomic structure and found a fascinating but still perplexing answer. Researchers discovered that the pillar is protected by a thin, invisible layer called a passive film. This film, only a few molecules thick, forms a barrier between the iron and the oxygen and moisture in the air, effectively putting corrosion on pause. The key to this film lies in the pillar's unique chemical recipe. Ancient Indian smiths, using a traditional furnace called a bloomery, produced iron with an unusually high phosphorus content and a very low sulfur content. This precise imbalance, a happy accident of their specific ore and process, is what encourages the protective film to form and regenerate over time. The scientific puzzle is solved in a sense. We know why it does not rust, but the deeper engineering mystery remains. How did they consistently produce such a large, homogeneous mass of wrought iron with these exact properties? Forging a 6-ton pillar is a monumental task of heating, hammering, and welding smaller pieces together. Yet the pillar shows remarkable uniformity. Replicating this today with historical methods is not straightforward. We can analyze the pillar, but we cannot easily recreate the lost, nuanced art of the smiths who made it. Their technique was a perfect synergy of material, method, and perhaps even an unwritten understanding of the process, turning a potential flaw into a feature of eternal endurance. This mastery of metal on a grand scale forces us to look for other artifacts where ancient metallurgy seems to leap ahead of its time, where the object in hand feels impossibly out of place. But a rust-resistant pillar is a marvel of chemistry, not necessarily of intricate design. For a true leap into the unknown, we must look to an object that should not exist at all. In the quiet of a museum in Athens rests a corroded lump of bronze and wood, recovered from a Roman shipwreck off the Greek island of Antikythera. For decades after its discovery in 1901, it was considered an unremarkable piece of nautical debris. Then researchers began to clean it and look closer. X-ray and later three-dimensional scanning revealed the truth. Inside was a clockwork universe. The Antikythera Mechanism is a complex assembly of over 30 precisely cut bronze gears, all housed in a wooden case no larger than a shoebox. It is, without dispute, the world's first known analog computer. Its dials and pointers, driven by an intricate gear train, could predict the positions of the Sun, the Moon, and likely the 5 known planets. It could forecast lunar and solar eclipses and even model the irregular orbit of the Moon, a small, hand-cranked machine that displayed the mechanics of the heavens. The date of the shipwreck places its construction around 2,100 years ago, and that is the heart of the mystery. This level of mechanical sophistication, this fusion of precise astronomy with miniature engineering, simply vanishes from the historical record after this device. Nothing remotely as complex appears again until the astronomical clocks of medieval Europe over 1,000 years later. It is not just ahead of its time, it is an isolated island of genius in a vast sea of time. Researchers have spent decades painstakingly reconstructing its functions from the fragments, and each new scan reveals more subtlety. The gears include a unique differential turntable, a component thought to have been invented in the 16th century that allowed it to account for the Moon's variable speed. The inscriptions on its casing are essentially a user manual detailing cycles and phenomena. This was not a one-off experiment. It implies a workshop, a school of thought, a tradition of geared technology that flourished and then was utterly lost. Who were these engineer philosophers? What other devices did they build? The mechanism's very existence rewrites a chapter in the history of technology, suggesting a parallel path of mechanical science that was snuffed out, leaving only this single, salvaged clue at the bottom of the sea. It forces a profound question. If they could build this, what else did they know how to make? This mastery of complex systems stands in stark contrast to another ancient achievement, one where the mystery lies not in intricate gears, but in the creation of a seemingly simple material that modern science has struggled to perfectly replicate. While the Antikythera Mechanism represents a pinnacle of delicate machinery, another Roman innovation endures through brute chemical strength. Modern concrete, the skeleton of our civilization, has a critical weakness. Exposed to seawater, it slowly breaks down as salt corrodes its internal steel reinforcement and causes the material itself to crack and crumble. Yet walk along the Mediterranean coast to the ancient harbor of Caesarea, built by Herod the Great over 2,000 years ago. There, submerged breakwaters made of Roman concrete still stand against the relentless sea, having outlasted entire empires. This is not luck. It is a material science puzzle that modern researchers only began to crack in the last decade. Our concrete uses Portland cement, which reacts with seawater in a destructive way. Roman concrete was different. Its recipe was a mix of lime and a specific volcanic ash called pozzolana, often hauled from the Bay of Naples. For centuries, we knew the ingredients, but not the magic. The breakthrough came when scientists analyzed core samples from these marine structures with advanced microscopes. They discovered tiny, plate-like crystals growing within the ancient mixture, a mineral called aluminous tobamorite. This crystal forms as seawater slowly seeps into the concrete, reacting with the lime and ash over decades and centuries. The process is transformative. Rather than causing decay, the seawater actually makes the Roman concrete stronger over time. These interlocking crystals act as a reinforcing armor, filling in micro-cracks as they form. In essence, the material heals itself. The Romans achieved this through empirical mastery, a recipe perfected by trial and observation over generations. They had no understanding of crystalline chemistry, but they knew this particular mix, when combined with seawater, created something eternally durable. The modern puzzle is not just the recipe, but the protocol, the exact ratios, the mixing method, the sequence of combining materials, and even the type of seawater used may have been crucial trade secrets lost with the empire's fall. We can now mimic the chemical result in a lab, but replicating the full, scalable, and efficient construction process that built harbors across the Mediterranean remains elusive. This concrete did not just build walls, it conquered the sea itself, creating permanent footprints where land met water. And this mastery of liquid environments leads to an even more audacious question. If they could make harbors immortal, what other hydrological wonders did they engineer? Roman concrete conquered the liquid frontier, but another ancient culture performed an even greater act of inscription upon the earth itself. The Nazca lines of Peru transform hundreds of square kilometers of barren desert into a sprawling, cryptic canvas. While their purpose fuels endless debate, their creation presents a separate, staggering engineering puzzle. These are not small sketches, they are monumental geoglyphs, some lines running arrows straight for over 30 miles across rocky, uneven ground. A hummingbird stretches over 300 feet. A spider measures 150, a condor's wingspan nears 400 feet. The precision is breathtaking. The shapes are perfectly proportioned, their curves smooth, and their junctions exact, as if drawn by a giant's steady hand. And this is the core of the mystery. The artists who created them between 2,000 and 1,500 years ago could never have seen their work from above. They executed these colossal designs while standing on the ground, with the horizon as their only reference. How do you draw a perfect spiral or a symmetrical monkey when you are standing on its toe? The prevailing theory involves a master plan scaled up from a smaller sketch. Using simple ropes, wooden stakes, and basic geometry, a team could have plotted key points and then cleared the dark surface stones to reveal the lighter soil beneath, following the guidelines between markers. This sounds plausible until you consider the sheer scale and the terrain. Maintaining a straight line for 10 miles over hills and gullies, ensuring it does not drift even a few degrees, becomes a feat of surveying that challenges modern intuition without a laser or transit. A single misaligned stake could throw the entire figure into distortion. The logistical coordination required is immense, suggesting a highly organized society with specialized surveyors who possessed a profound, practical understanding of geometry and spatial relationships. They worked with the landscape as a partner, using the long, straight valleys between hills as natural guide paths for the longest lines. This was not random art. It was a systematic, generations-long project of terrestrial engineering, a dialogue with the desert floor that resulted in images only the sky could fully comprehend. This act of reshaping the very land on a geographical scale finds a strange and inverted parallel in another part of the world, where the earth itself was not marked, but was instead moved in a pattern so vast it defies ground-level understanding. The Nazca artists worked on a canvas only visible from the heavens, but on a remote island in the Pacific, a civilization created giants meant to be seen from the ground. Easter Island's Moai statues stand as silent, brooding sentinels, their blank eyes gazing inland from stone platforms along the coast. Each of these figures is a single, carved monolith, with the average one standing about 13 feet tall and weighing around 14 tons. But the true marvels are the giants. The largest Moai ever erected, named Paro, is nearly 33 feet tall and weighs an estimated 82 tons. And then there is the unfinished Colossus still lying in the quarry, which would have stood an astonishing 70 feet tall, and weighed close to 270 tons. The central, haunting question is not how they were carved, but how they were moved. The Ronoroku quarry, where all the Moai were born, is a volcanic crater. From this central point, finished statues were transported across miles of rugged, rolling terrain to their final ceremonial platforms called ahu, some journeys stretching over 10 miles. With no large trees for rollers and no evidence of complex machinery, the method of transport has become one of the world's most famous archaeological puzzles. For decades, the dominant theory was that the Rapa Nui people laid the statues flat and dragged them on wooden sledges or log rollers using teams of ropes. This method, while plausible, presents severe problems. The island's landscape is not flat. It is a patchwork of hills, soft soil, and sharp volcanic rock. Dragging an 80-ton stone block over such ground would be incredibly difficult, likely causing deep grooves and requiring an immense workforce to constantly reposition logs. More critically, this theory contributed to a now outdated narrative of ecological suicide, suggesting the islanders cut down every last tree to make rollers, collapsing their own society. More recent and revolutionary thinking proposes something far more dynamic and clever. Researchers, drawing on local oral tradition that said the statues walked to their places, have tested a method of upright transportation. By using 3 strong ropes tied around the statue's head, teams could rock a moai from side to side, pivoting it on its base like a person shuffling their feet. In a famous experiment, a team of just 18 people with careful coordination managed to walk a 10-foot-tall, 5-ton concrete replica several hundred yards. This method feels intuitively right, matching the legends and seeming more manageable over uneven ground. But it is not a perfect solution either. Critics point out that the real moai have broad, sloping bases not ideal for pivoting, and that the process would place tremendous stress on the statue's neck, which is its thinnest point. Many moai found along the ancient roads are in fact broken, lying face down. Were these casualties of the walk? Another emerging theory suggests a hybrid approach, using a wooden sledge or cradle, but on prepared roads. Archaeologists have indeed found ancient roads radiating from the quarry, some with a concave, U-shaped profile that could have helped guide and stabilize a moving load. The definitive answer remains just out of reach. Each experiment shows a possibility, but also raises new logistical questions. The true method was likely as sophisticated as the society that devised it, a carefully guarded technique of physics and rhythm, of chance and coordinated pulls, lost with the last master mover. This monumental effort was not just about moving stone, it was about connecting the community to the cosmos, placing these ancestors in precise alignment with the world around them. And that desire to engineer a connection to the heavens is a thread that runs through countless ancient cultures, manifesting in structures that are not just tombs or temples, but precise celestial calendars built in stone. The silent giants of Easter Island were moved across land by a society with a singular vision. But in Britain, an earlier monument presents a transport puzzle that spans land, river, and sea. Stonehenge's iconic outer circle of sarsen stones is a local marvel, but the first stones erected there, the smaller Bluestones, are geological foreigners. Their specific type of spotted dolerite is found only in the Preseli Hills of West Wales, a staggering 140 miles away from Salisbury Plain. This is not a question of why they built it, but a profound logistical mystery of how they got the stones there in the first place, over 5,000 years ago. Each of these Bluestones weighs between 2 and 4 tons, not as massive as a moai, but their journey is measured in marathon distances, not miles. The debate among archaeologists is a lively one, essentially a contest between human ingenuity and natural forces. One school of thought champions a purely human effort, a monumental trek. This theory envisions teams dragging the stones on wooden sledges across the rugged landscape of prehistoric Britain. They would have had to navigate steep hills, thick forests, and soft, boggy ground, a journey that could have taken months for each stone. To ease the burden, another hypothesis proposes a hybrid route. The builders might have hauled the stones to a nearby river, loaded them onto rafts, and floated them along the Welsh coast and up English rivers, finally dragging them overland the last short distance to the site. This water highway theory seems efficient, but it introduces its own dangers, like navigating treacherous coastal waters and river currents with an irreplaceable multi-ton cargo. A more controversial idea suggests that perhaps humans did not move the stones at all, that glaciers during the last ice age carried the Bluestones south and deposited them much closer to Salisbury Plain, where Neolithic people simply collected them. Recent geological studies, however, strongly indicate the stones came from very specific outcrops in the Preseli Hills, not from a scattered glacial field, making the human-led theories far more compelling. Regardless of the method, the organizational feat is staggering. It implies a society with the authority to command labor and resources across a vast territory, and the technical skill to manage a supply chain spanning different ecosystems. This effort raises the most tantalizing question of all. Why go to such extraordinary lengths for these particular stones? The Preseli Hills were a sacred landscape, home to ancient springs and other monuments. It seems the builders did not just want any stone, they needed this stone, imbued with the spiritual essence of a distant, powerful place. They were not merely constructing a calendar, they were physically uniting their world, bringing a piece of a holy mountain to the center of their cosmos. This act of astronomical alignment through imported stone finds a breathtaking parallel in another ancient culture, one that did not move stones across a landscape, but instead carved an entire mountain into a perfect, silent clock. The desire to capture a single moment of celestial light required engineering on a breathtaking scale. In the rolling green landscape of Ireland's Boyne Valley, a massive circular mound of earth and stone has stood for over 5,000 years, making it older than Stonehenge and even the Great Pyramids of Giza. This is Newgrange, a passage tomb built by a Neolithic farming community with a profound connection to the cycles of the sun. Its most famous feature is not its size, but a small, seemingly insignificant architectural detail above the main entrance. This is the roof box, a narrow, rectangular opening framed by large stone slabs, set just below the edge of the grass-covered roof. It looks like a deliberate window, but its purpose remained a modern mystery for centuries after the tomb's rediscovery. Then, on the winter solstice of 1967, an archaeologist stood inside the long, dark central chamber and witnessed the true intent of the ancient builders. As the sun crested the horizon on that shortest day of the year, a slender beam of golden light pierced the darkness. It entered through the roof box, traveled down the 60-foot-long stone-lined passageway, and for approximately 17 precious minutes, flooded the inner chamber with a direct, radiant glow, illuminating spiral carvings deep in the heart of the mound. This was no accident. Achieving this annual event required staggering precision. The entire mound, over 280 feet in diameter, had to be constructed with the passage oriented precisely to the southeast, aligning with the solstice sunrise on that specific azimuth. The roof box itself is a feat of engineering, a carefully stabilized aperture that ensures the light beam enters at the correct angle and travels the full length of the corridor without being blocked by the structure itself. This implies the builders possessed not only advanced observational astronomy, marking the sun's lowest point in the sky year after year, but also the architectural skill to translate that knowledge into a permanent, massive structure designed to function for millennia. They planned for an event they would never personally witness in its completed form, embedding a calendar in stone and earth that would outlast their language and their names. This mastery of aligning massive architecture with celestial precision finds a parallel not in another monument to the sky, but in a civilization that turned its engineering genius inward, carving not tombs, but entire cities from the living rock beneath their feet. Deep beneath the fairy tale landscape of Cappadocia lies a world turned inside out. The Derinkuyu underground city is not a simple cave or a single refuge. It is a vertical metropolis carved into soft volcanic rock, descending over 200 feet through at least 18 distinct levels. This was not a temporary hiding place. It was a designed habitat capable of sheltering thousands of people along with their livestock and food stores for extended periods. The most immediate and lethal challenge for such a deep, enclosed space is not darkness or space, but the very air itself. Without a constant supply of fresh air, the inhabitants would face a silent, invisible threat within hours. The engineering solution they devised is a masterpiece of passive environmental control. Over 50 individual ventilation shafts, some as wide as a person, were drilled from the deepest chambers all the way up to the surface, often disguised within natural rock formations or concealed courtyards above. These were not just simple holes, they functioned as a sophisticated circulatory system for the entire city. The principle is one of thermodynamics. Warm, stale air from the crowded living quarters and animal pens deep below would naturally rise, seeking an exit. The strategically placed shafts provided that exit, creating a steady updraft. This rising column of warm air then pulled cooler, fresh air from the surface down through other dedicated intake shafts, creating a continuous, gentle breeze throughout the labyrinth. They even engineered the shafts to have slightly different diameters and heights to optimize this airflow, a subtle understanding of fluid dynamics achieved through observation and trial. This network ensured breathable air reached even the lowest storage chambers and wineries 70 meters down. The ventilation is just one part of a staggering planning puzzle. Excavating this city required a precise blueprint executed in 3 dimensions, accounting for structural stability to prevent collapses, designing a network of rolling stone doors to seal off sections, and integrating water wells, kitchens, churches, and stables all within a stable, breathable, and psychologically manageable environment. It represents a complete inversion of city planning where every necessity had to be engineered from scratch, not built upward, but carefully carved downward with the confidence that the air would follow. This profound understanding of how to shape the earth for large-scale communal living finds a striking contrast in another ancient urban achievement, one that faced the opposite problem, not carving shelter from rock, but summoning life-giving water to a city built entirely in the open air. The air that flowed through Derinkuyu's hidden chambers was a triumph of subterranean design, but another ancient civilization mastered the art of connection across the open air. The Inca Empire's greatest engineering feat was not a single city, but the very veins that held its vast territory together. The Quhapacñan, or Royal Road, is a staggering network of pathways stretching over 24,000 miles from the cloud forests of Colombia to the arid plains of Chile. While its sheer scale is breathtaking, a more subtle mystery emerges when you walk its path. Across some of the most punishing terrain on Earth, the road runs in knife-straight lines for miles at a stretch. In the Andes, a landscape of jagged peaks, deep canyons, and unstable slopes, this insistence on straightness is an engineering puzzle that defies common sense. It would have been far easier and seemingly more logical for the road to wind and switch back following the natural contours of the mountains, but the Inca engineers refused this compromise. They built causeways across swamps, carved staircases into sheer cliff faces, and constructed retaining walls hundreds of feet high to maintain their direct routes. Achieving this precision required a level of surveying that seems almost supernatural. Without magnetic compasses, theodolites, or even the wheel, how did they plot these lines across such vast and broken distances? Researchers believe they used a combination of simple, brilliant tools and profound environmental knowledge. They likely employed sighting poles called saywers placed on high ridges. By aligning these poles with distant landmarks like mountain peaks or specific stars, they could project a straight line across the horizon. This method turned the entire landscape into a living map, using the immutable features of the earth and sky as their guide points. The straightness served a critical, urgent purpose: speed. This was the backbone of the empire's communication system, the Chasqui relay. A message or fresh fish from the coast could travel over 200 miles in a single day, as runners sprinted between small posts spaced about a mile apart. A straight road meant the runner always had the next post in sight, minimizing hesitation and maximizing efficiency. The empire's authority literally depended on the line of sight. But this benefit came at an immense cost of labor and ingenuity. Every straight segment demanded a brutal negotiation with geology, a testament to an imperial will that valued swift control over construction ease. This mastery of terrestrial pathways, of moving people and information with purpose, finds its logical counterpart in a different kind of engineering, one that moved not people, but the most vital resource of all, water itself. The straight roads of the Inca moved people, but another civilization perfected the art of moving water with invisible precision. Across the arid plateaus of ancient Persia, survival depended on a hidden network of veins known as the qanat. These were not open canals, but underground aqueducts, hand-dug tunnels that tapped into groundwater at the base of mountains and transported it for dozens of miles across the desert, using nothing but the silent, relentless pull of gravity. The engineering puzzle lies in the slope. To make water flow, the tunnel must descend from the source to the destination at a constant, gentle grade. Too steep, and the water would rush through, eroding the tunnel walls and wasting the precious resource. Too flat, and the water would stagnate, becoming foul and useless. The Persian engineers achieved this perfect gradient, often as little as a 1 in 1,000 slope, over distances that could span 50 kilometers, all without theodolites, lasers, or even simple spirit levels as we know them. How did they survey such a precise path through solid earth and rock? The method was a masterpiece of simple tools and profound patience. First, master surveyors, known as mukanis, would identify a water-bearing layer at the foot of a mountain. Then they would determine the destination point, often a settlement or an agricultural field far out on the plain. The critical task was plotting the straight line between them, but one that sloped downward at exactly the right rate. They likely used a series of shallow, temporary surface channels and primitive water-filled trenches to establish a level reference over short distances, transferring that benchmark down as they went. The real construction began with a paradox. Instead of digging from the source to the destination, teams started at the destination and worked backward, tunneling into the hillside. At regular intervals, sometimes every 20 to 30 meters, they dug vertical access shafts straight down from the desert surface to meet the growing tunnel below. These shafts served a dual purpose. They provided ventilation for the diggers, removed excavated material, and most ingeniously, acted as a built-in surveying system. By measuring the depth of each successive shaft, the builders could constantly check their gradient. If a new shaft was not a precise, predictable amount deeper than the last, they knew they had strayed off the correct slope underground and could correct their course. This was engineering by iteration and constant verification, a project that could take generations to complete. The sustainability of the qanat is perhaps its most brilliant feature. Because the water flows in a sealed underground channel, evaporation in the scorching desert sun is nearly zero, and contamination is minimal. For over 3,000 years, these systems have sustained oasis cities across the Middle East and beyond, a testament to a technology that worked in harmony with the physics of the earth itself. This quiet mastery of hydrology finds a louder, more dramatic expression in another part of the ancient world, where water was not just channeled, but commanded to perform in spectacular public displays. The qanat's gentle gravity-fed flow sustained life in silence, but in the coastal deserts of ancient Peru, water was a resource to be seized and commanded on a monumental scale. The Moai culture, flourishing from about 100 to 800 CE, faced an environment that seems almost impossible for agriculture. Their homeland was a narrow strip of land between the Pacific Ocean and the Andes Mountains, a landscape where rain might not fall for years at a time. Yet here they built thriving cities and produced abundant harvests. Their secret was not magic, but a masterwork of hydraulic engineering, an intricate web of canals that turned barren desert into a vast, fertile garden. These were not simple ditches. The Moai canal networks were complex, branching systems that captured water from seasonal rivers flowing down from the Andes and redistributed it across the coastal valleys with breathtaking efficiency. Some of these canals stretched for over 60 miles, traversing difficult terrain of rock, sand, and shifting slopes. The engineering puzzle lies in their precision. To make water flow reliably over such distances, the canals had to maintain a very specific, consistent gradient, just like the Persian qanats, but here the channels were largely open to the air and sun. Calculating and maintaining that perfect slope across miles of uneven desert, using only simple tools and human sight, required an intimate, generations-deep understanding of hydrology and surveying. They built aqueducts to cross gullies and constructed massive diversion dams to control the fierce flow from the mountain rivers during rare rain events. Perhaps their most ingenious innovation was their understanding of sedimentation. The water coming from the Andes was heavy with silt and sand, which could quickly clog and fill a canal. The Moai engineers designed their systems with settling tanks and clever changes in the canal's speed and direction to allow this sediment to drop out before the clearer water continued onto the fields. This not only kept the canals flowing, but the collected silt, rich in minerals, could then be used to fertilize the very soil they were irrigating. It was a closed-loop system of astonishing foresight. The scale of this transformation is almost unimaginable. Researchers estimate that at their peak, these canal networks irrigated over 150,000 acres of land, supporting a large, urbanized population. The sophistication rivals modern irrigation districts, yet it was built without metal tools, without written plans, and powered entirely by coordinated human labor. This represents a pinnacle of practical, applied engineering knowledge, a school of thought focused on reshaping the world to sustain life. That knowledge, however, was not just about moving water. It was about harnessing a fundamental force of nature, a principle that leads to a far more speculative and mysterious realm of ancient thought. For if some cultures could so perfectly command the flow of water, did others believe they could tap into even more elusive currents, the unseen energies of the earth itself? The mastery of visible forces like water makes the possibility of an ancient grasp of invisible energy all the more tantalizing. In the 1930s, during excavations near Baghdad, workers uncovered a set of peculiar objects that would ignite a debate lasting to this day. The artifacts are simple in form, a small clay jar about the size of a fist sealed with asphalt. Inside each jar sits a rolled copper cylinder, and within that cylinder an iron rod. The materials alone are not mysterious, but their specific assembly is. When a German archaeologist examined them years later, a startling hypothesis emerged. If this jar were filled with an acidic liquid like vinegar or grape juice, the chemical reaction between the electrolyte and the two dissimilar metals could produce a small electrical charge. In essence, it could function as a primitive galvanic cell, a battery. Dating places these objects to the Parthian period, around 2,000 years ago. The immediate question is electrifying. Could this be evidence of ancient electroplating? The theory suggests that several of these cells linked together could provide enough current to deposit a thin layer of gold or silver onto another metal object, a technique known as gilding. Some proponents point to artifacts from the region that show exceptionally fine gold coatings, suggesting a method beyond simple mercury amalgam. Yet, here the evidence becomes frustratingly thin. No wires, no connectors, and no electroplated objects were found alongside the jars. No contemporary texts describe such a process. Other theories drift into more speculative realms, proposing the mild shock was used for medicinal purposes, a form of ancient analgesic, or even to create a tingling sensation during religious ceremonies, a tangible spark of the divine. The sobering counterpoint is that these objects could simply be storage vessels for sacred scrolls, with the iron rod acting as a core and the asphalt as a sealant, with no electrical intent at all. This is the heart of the puzzle. We have an object that can function as a battery, but we lack any proof it ever did. If it was purposeful, it represents a stunning, isolated spark of electrochemical knowledge that appears to have no lineage, no development, and no clear application in the archaeological record. It is a concept without a context, a single, quiet question mark in the history of technology. It forces us to wonder how many other potential discoveries were lost because their purpose was not obvious, or because we are looking for the wrong kind of evidence. This mystery of potential energy, of a current that may or may not have ever flowed, finds a fascinating parallel in another ancient engineering discipline, one that dealt not with electricity, but with the deliberate and powerful manipulation of sound itself. Sound itself becomes a tangible, architectural material in the silent depths of Malta. Beneath the island's modern streets lies the Hal Saflieni Hypogeum, a Neolithic underground temple complex carved from solid limestone over 5,000 years ago. This is not a simple cave network. It is a three-level labyrinth of interconnecting chambers, halls, and alcoves, meticulously sculpted to mimic the megalithic temples found above ground, complete with carved pillars and false doorways. But its most unsettling feature is not its appearance but its sound. Within certain chambers, particularly the oval-shaped oracle room, the acoustics behave in ways that feel impossible. If a person speaks in a deep, resonant voice at a specific pitch, the sound does not just echo. It amplifies, vibrating through the stone with an intensity that can be felt in the bones. The entire chamber seems to hum, the frequency filling the space and lingering long after the voice has stopped. Modern acoustic analysis has confirmed this phenomenon. The room is tuned, almost like a musical instrument, to powerfully resonate at a frequency around 110 Hz, a low, droning tone. Research into the effects of such frequencies on the human brain suggests they can alter states of consciousness, potentially inducing feelings of focus, trance, or heightened awareness. Given the hypogeum's clear function as a ceremonial and resting place, the implication is profound. The builders likely shaped these rooms not just for visual ritual, but for sonic experience. They engineered an environment where sound could become a direct pathway to the sacred. The puzzle is how they achieved this precision. Without oscilloscopes or tuning forks, how did Neolithic artisans carve a room to perfectly amplify one specific note? Some researchers suggest it was a product of trial and error over generations, a slow refinement of space based on observed effect. Others propose the builders possessed an intuitive, empirical understanding of resonance, perhaps discovering the ideal proportions through chanting or drumming within the stone itself. The architecture itself guides the sound, with curved walls focusing the waves and niches acting as sound baffles. This was not an accident. It was acoustic engineering of the highest order, turning the earth into a resonator for the human voice, a technology of vibration whose principles we can measure but whose discovery remains shrouded in the preliterate dark. This intentional design of sound for ritual purpose finds a startling and much louder echo thousands of miles away, where an entire mountainside was engineered to project not a hum but a thunderous roar. The silent hum of Malta's hypogeum finds a spectacular public counterpart in the bright sunlight of the Yucatan. At the great Mayan city of Chichen Itza, the Pyramid of Kukulkan holds a secret that is not seen but heard. If you stand at the base of the monumental staircase and clap your hands once, sharply, the stone responds. The echo that returns is not a simple repetition of the clap. It is a crisp, descending chirp, a sound that uncannily mimics the call of the sacred Quetzal bird, a creature of immense spiritual significance to the Maya, associated with the feathered serpent god Kukulkan himself. This is not a vague resemblance, it is a precise acoustic phenomenon, reproducible every time. The engineering behind this avian echo is a masterpiece of applied physics, written in stone. The towering staircase is not just a set of steps, it functions as a sound diffraction grating. When the sound wave from the clap hits the staircase, it does not reflect off a flat surface. Instead, it strikes the series of evenly spaced vertical step faces. Each step reflects a tiny portion of the sound wave back to the listener, but because each step is slightly farther away, each reflected wave arrives at the listener's ear a fraction of a second later than the one before. Our brain perceives this rapid series of microechoes not as distinct sounds, but as a single, pitched chirp with the frequency dictated by the precise spacing between the steps. The timing is everything, and the pyramid's geometry provides it with mathematical perfection. This raises the profound and persistent question: was this a deliberate design or a breathtakingly fortunate accident? The alignment is so perfect, and the resulting sound so specifically tied to a sacred animal, that many researchers find coincidence difficult to accept. It suggests the Maya architects possessed not only advanced knowledge of astronomy and geometry, which they clearly did, but also a sophisticated, empirical understanding of acoustics. They may have discovered this principle through observation and ritual practice over generations, slowly refining the proportions of their structures to harness sound as a spiritual tool. The pyramid itself becomes a divine instrument, a stone whistle activated by human interaction, blurring the line between architecture, nature, and the divine. This intentional marriage of form, function, and sacred symbolism points to a holistic view of engineering, where a structure must satisfy not just the eye, but the ear and the soul. Such a comprehensive design philosophy naturally extends its reach beyond the earth, aiming to capture and reflect the grandest patterns of all, those written in the movement of the stars. The same desire to inscribe celestial time onto stone appears in a place of stark, silent beauty. High atop Fajada Butte in New Mexico's Choco Canyon, the ancestral Pueblones engineered a calendar not with moving parts but with light and shadow. Here, 3 massive stone slabs, each weighing several tons, lean against a south-facing cliff wall. Carved into the rock behind them is a set of spiral petroglyphs, elegant and precise. For most of the year, this arrangement seems unremarkable, but on specific days, the sun itself performs a silent, breathtaking ritual. As the sun climbs, its light filters through the narrow gaps between the 3 giant slabs. Instead of casting a simple beam, the precise geometry of the gaps sculpts the light into distinct shapes. At the summer solstice, a sharp, dagger-like slash of sunlight appears and bisects the center of the largest spiral. At the winter solstice, 2 perfect daggers of light bracket the same spiral. On the spring and fall equinoxes, a single dagger of light pierces a smaller spiral to the side. This is the sun dagger, a celestial timepiece carved into the living rock of the desert. The engineering puzzle is one of monumental precision. Someone had to position those multi-ton slabs, not randomly, but with the exactitude of a master watchmaker. The angles of their tilt, the width of the gaps between them, even their distance from the cliff face, all had to be calculated and set perfectly to create those specific light patterns at those exact moments of the year. This required not just an understanding of the solar cycle, but an ability to translate that knowledge into a permanent, physical installation on a colossal scale. The mystery deepens when you consider the full scope of its function. Researchers studying the site realized the light patterns do more than mark the solstices and equinoxes. They also track a much slower, more subtle cycle, the 18.6-year lunar standstill cycle. This is the period it takes for the moon's rising and setting points to complete a slow migration across the horizon. Somehow, the ancestral Pueblones encoded this long-term lunar rhythm into the same stone arrangement, a feat of observational astronomy that implies generations of careful record-keeping. The true testament to their skill, however, may be the site's fragility. In the late 20th century, shifting of the slabs, possibly due to erosion or human interaction, altered the alignment. The perfect daggers of light no longer strike their targets with the original surgical accuracy. This disturbance, while a loss, underscores the incredible precision the builders originally achieved. It was a delicate, dynamic equilibrium of stone and sunlight, a masterpiece of archaeoastronomy that functioned for centuries as a silent, reliable keeper of cosmic time for the people of Chaco. The silent precision of the sun dagger required a perfect marriage of stone and celestial motion. But in China, a different kind of carved precision exists on a scale that is almost industrial. Deep within the Zhejiang province, hidden beneath unassuming hills, lie the Longyou caves, discovered by chance in 1992 when a local farmer pumped water out of what he thought was a small pond. They revealed themselves as something staggering. This is not a single cavern, but a network of at least 24 massive hand-carved rooms, each one an enormous subterranean hall. The largest spans over 12,000 square meters, with pillars left in place to support ceilings that soar up to 30 meters high. The sheer volume of rock removed is estimated at 1 million cubic meters, a labor so immense it defies comprehension. Yet the engineering mystery is not just the scale, but the eerie, machine-like consistency of the work. Every single surface across every chamber is covered in a uniform pattern of parallel chisel marks. These grooves, each about the width of a hand, are carved at a precise, consistent 60-degree angle, running in neat, unbroken bands across walls, pillars, and ceilings. It looks less like the work of individual stonecutters and more like a giant mechanical rake was dragged through the soft sandstone. This uniformity is the central puzzle. How did a large workforce, presumably working with simple iron tools by torchlight, maintain such a rigid, unvarying standard across what must have been generations of labor? There is no deviation, no change in technique from one cave to the next. This suggests a master plan and a strictly enforced methodology, a level of project management and quality control we rarely associate with such an ancient, undocumented endeavor. The purpose of these colossal spaces remains a complete enigma. They show no signs of habitation, no burials, no religious iconography. The consistent markings are not decorative, they are simply the byproduct of the excavation method itself. This leads to the most perilous engineering question of all. The rock is a fragile, water-saturated sandstone. How did the planners know where to carve, how to shape these vast spaces, and how to leave just the right pillars in just the right places to prevent a catastrophic collapse? They left no blueprints, no maps. The caves stand today, 2,000 years later, as a testament to a lost school of underground engineering. A project of such coordinated ambition that its very reason for being has been swallowed by the silence it created. This act of carving order from chaos within a mountain finds a strange parallel in another part of the world, where the rock itself was not hollowed out, but was instead assembled into forms that seem to defy the very weight they carry. The Longyou caves present a puzzle of immense, uniform removal. But in India, another excavation turned subtraction into a form of worship so audacious it redefines the word sculpture. The Kailasa temple at the Ellora caves is not a built structure. It is a mountain that was persuaded to become a temple. Around 1200 years ago, under the Rashtrakuta dynasty, master planners stood before a solid basalt cliff face and envisioned a complete Hindu temple complex within it. Their method was not to add stone, but to remove it with the confidence of someone revealing a statue hidden inside a block of marble. The difference is scale. They did not carve a statue, they carved an entire freestanding temple, courtyards, pillars, galleries, and all from the top down. The numbers are staggering. Archaeologists estimate that over 200,000 tons of rock were painstakingly chiseled away, hauled out, and discarded. That is more than twice the volume of the Great Pyramid of Giza. But here, the material was not brought to a site, it was taken away from one. The logistical challenge of this subtractive construction is mind-bending. To carve a multi-story temple with internal staircases, a main shrine, and life-sized elephant sculptures, all from a single piece of living rock, you cannot make a single critical error. There is no undo button. If you cut too deep in the wrong place, you cannot add stone back. This required a master blueprint of incredible foresight, likely laid out on the cliff face itself, a three-dimensional plan held in the minds of the chief architects and passed down through generations of artisans. The waste removal alone was a monumental task. Teams of workers had to cut the excavated basalt into manageable blocks, lower them from ever-increasing depths, and transport them away, all while the temple itself was emerging from the void they were creating. The precision is visible in the delicate, intricate sculptures that adorn every surface, from the epic friezes depicting Hindu mythology to the geometrically perfect pillars that line the courtyards. They achieved this not with power tools but with simple chisels and hammers, guided by a vision so complete that the temple appears to have grown from the ground, rather than being revealed by removal. It stands as the ultimate testament to a philosophy of engineering as revelation, a belief that the divine form was already present within the stone, waiting only for human hands, faith, and unimaginable patience to set it free. The concept of carving a mountain into a temple is an act of profound faith in a master plan. But at another Andean site, the stones themselves seem to speak of a plan so technical it feels out of place. On the high plateau of Bolivia, near the shores of Lake Titicaca, lie the scattered ruins of Puma Punku, part of the ancient Tiwanaku complex. What remains here is not towering walls or grand pyramids, but a field of shattered, intricately carved stone blocks that look less like ruins and more like the components of a giant, disassembled machine. The most iconic pieces are the so-called H-blocks, massive slabs of andesite and granite, each weighing many tons. What makes them an enduring engineering puzzle is not their size, but their impossible precision. Each block is cut with a series of complex geometric recesses and protrusions. The surfaces are not just flat, they are perfectly planar, as if milled by a modern machine shop. The edges are razor-sharp, meeting at perfect 90-degree angles. Most baffling are the intricate channels and notches cut into the stone with surgical accuracy. Some of these channels are T-shaped slots, while others are dovetail joints or precise L-shaped cuts, all clearly designed to interlock with other, now missing, pieces using a form of metal clamps. The stone itself deepens the mystery. Andesite is an exceptionally hard, dense volcanic rock, ranking just below diamond on the hardness scale. To cut, shape, and polish it to this level of perfection would be a formidable challenge even with today's powered diamond-tipped tools. Yet the builders of Puma Punku did it repeatedly on an industrial scale, with a consistency that suggests a standardized, repeatable process. The purpose of this insane joinery is completely unknown. These were not mere building blocks stacked with mortar. The complex interlocking system implies the structure could withstand tremendous lateral force, perhaps seismic activity, or that it was meant to be taken apart and reassembled. The uniformity of the cuts suggests the use of templates, a kind of mass production in stone. This has led to intense speculation. Could the Tiwanaku culture have possessed lost high-tech tools, perhaps using some form of abrasive slurry with saws under immense pressure, or even techniques involving focused heat? Other researchers point to the possibility of an advanced, purely empirical stone working knowledge, a school of craftsmanship that understood the properties of their materials intimately and developed specialized tools and methods over centuries, methods that were lost when their civilization declined. The stones of Puma Punku do not whisper of gods or kings, they whisper of engineers and draftsmen. They represent a puzzle where the question is not why, but specifically how, a question that makes us wonder if an entire chapter on ancient fabrication technology is missing from our history books. While the stones of Puma Punku suggest a lost school of industrial precision, Egypt offers a structure that feels like a ghost from a different architectural age entirely. At the sacred site of Abydos, behind the magnificent temple of Pharaoh Seti I, lies a sunken, waterlogged chamber known as the Osirian. On the surface, it is attributed to Seti, meant as a symbolic tomb for the god Osiris. But to step inside is to experience a jarring discontinuity. The main temple is classic, refined New Kingdom architecture with elegant columns and detailed reliefs. The Osirian, just a short distance away, is something else entirely. It is a stark, powerful space built from colossal blocks of red granite, each one a monolithic slab weighing up to 100 tons. These giants form a central rectangular island, surrounded by a deep, water-filled trench, with more massive pillars holding up a roof of equally immense stone beams. The style is what archaeologists call Cyclopean, named for the mythical giants, characterized by enormous, minimally shaped stones fitted together with a raw, primal power. It looks nothing like the graceful, precise stonework of Seti's temple. It looks instead eerily ancient, as if it belonged to a much older, forgotten era of Egyptian history. This is the core of the engineering puzzle. If Seti I built it, why would he use a construction style that had been obsolete for over 1,000 years? The sophisticated, smooth-sided pyramids of the Old Kingdom were already ancient history by his time. The Cyclopean style is more reminiscent of the earliest, most experimental megalithic structures from a time before dynastic rules were fully established. The contrast is so severe that many researchers argue the Osirian is not a New Kingdom construction at all. They propose it is a pre-dynastic relic, a monument from a shadowy period before the first pharaohs, that Seti I simply discovered and incorporated into his own sacred complex. He may have built his temple behind it to honor and connect with this already ancient, venerated site. The evidence lies in the foundation itself, the construction technique, the sheer scale of the blocks, and the way they are positioned within the water table suggest a different engineering philosophy, one focused on permanence through mass and weight rather than refined joinery. The water-filled trench is also unique, possibly representing the primordial waters of creation in Egyptian myth, but its practical construction would have been a nightmare, requiring constant drainage during building. This creates a fascinating chronological rift. Within the well-documented timeline of Egyptian architecture, the Osirian sits like an anachronism, a piece of a much older puzzle deliberately placed at the heart of a newer one. Its true builders and the methods they used to maneuver these 100-ton granite sentinels into their watery chamber remain silent, leaving us to wonder what other foundational secrets are buried, quite literally, beneath the sands of time. That raw, primal power of the Osirian Cyclopean blocks forces us to look back at the very foundations of Egypt's most famous monuments. Before a single block of the Great Pyramid could be laid, its builders faced a more fundamental and often overlooked challenge. They had to conquer the ground itself. The Giza Plateau is not a naturally flat, featureless table. It is a sloping expanse of limestone bedrock, dotted with natural mounds, ridges, and depressions. To erect a structure demanding micrometer precision, they needed a foundation of absolute stability and perfect flatness. The area they prepared for the Great Pyramid's base spans over 13 acres. And across this entire sprawling footprint, they leveled the underlying bedrock to an accuracy within a few centimeters. Think about that for a moment. It is the equivalent of taking a plot of land larger than 10 football fields, and with nothing but copper chisels, stone hammers, and human labor, shaving down the very earth until it is as flat as a modern parking lot. How could they possibly achieve such a feat with such rudimentary tools? The most compelling theory involves a beautifully simple application of a basic principle: water always finds its level. Archaeologists suggest the builders dug a grid of shallow trenches across the construction site and filled them with water. By marking a consistent water line on the trench walls, they established a perfect horizontal reference plane across the entire area. Teams of workers could then painstakingly chip away any bedrock that stood above that water line, constantly checking their progress against this liquid guide. It was a method of staggering patience. Every inch of protruding stone had to be identified, quarried down, and removed. For low spots, they would have filled them with compacted rubble and mortar, building up to the required level. The coordination required for this initial phase is almost as impressive as the pyramid's construction. Hundreds, if not thousands, of workers had to operate in unison across the vast site, all guided by that single, silent standard of the water's surface. This was not brute force, it was controlled, systematic subtraction on a geological scale. It meant the pyramid's first and most critical course of stones would rest on a platform that was not just solid, but mathematically true, a guarantee of structural integrity for millennia to come. This foundational obsession with perfect flatness reveals a profound truth. The ancient engineers understood that their ambition could only rise as high as their foundation was steady. Every ounce of precision that followed, every flawless alignment of the rising courses, depended entirely on this first, back-breaking act of making the earth itself obey their will. The same obsession with a perfect foundation finds a more secretive and perhaps more puzzling expression deep beneath the sand. At Saqqara, the vast necropolis of ancient Memphis, a long, dark corridor descends into the earth. This is the Serapeum, an underground gallery dedicated to the sacred Apis bulls. But the true marvel here is not the resting place of the animals, but the containers built to hold them. Lining the passage are 24 monolithic boxes, each one carved from a single block of granite or diorite. These are not simple coffins. They are engineering artifacts of baffling precision. Each sarcophagus is a behemoth weighing over 70 tons, the equivalent of a modern main battle tank. They were quarried, transported, and lowered into this subterranean gallery, a feat in itself. But the real mystery is inside. The boxes are hollow. Their interiors are not rough-hewn chambers. They have been scooped out to create smooth, flat walls and floors, with corners that meet in razor-sharp, perfect 90-degree angles. The surfaces are so uniform and polished that they feel machined. The puzzle is one of fabrication. Granite is brutally hard, ranking just below diamond. The official tools of the Old Kingdom were copper chisels and stone hammers. A copper chisel would be useless against granite, blunting with every strike. Even with abrasive sand and a lot of time, the process of hollowing out a 70-ton block to create such flawless internal geometry seems almost insurmountable. How do you reach inside a solid block to carve and polish the far corners with such surgical accuracy? The logistical nightmare deepens when you consider their stated purpose. These sarcophagi were meant for the mummified remains of the Apis bulls, animals revered as incarnations of the god Ptah. Yet when the French Egyptologist Auguste Mariette rediscovered the Serapeum in 1851, he found the giant lids shoved aside and the boxes mostly empty, save for a few fragments of bone. The bulls that were found rested in much smaller, adjacent chambers. This creates a profound disconnect. The sarcophagi are colossal, their internal dimensions far too vast for a bull, even a sacred one. If their purpose was symbolic, why engineer them with such impossible, hidden precision? The effort invested in the invisible interior suggests a function or a standard that we no longer understand. Some researchers point to the box's resonant acoustic properties, wondering if their shape was designed for sound. Others see the handiwork of a lost technology, a method of working stone that allowed for controlled, almost fluid removal of material. The Serapeum presents a quiet, underground rebellion against our standard narrative of ancient capability. Here, the proof is not in a towering pyramid, but in a dark gallery of silent, perfect boxes, their true purpose sealed away as completely as their original content. The silent precision of those underground boxes speaks of a society with immense resources and a singular vision. But to find the very origins of that vision, we must travel back to a time before pharaohs, before writing, before even the widespread use of metal. In the Jordan Valley, the ancient settlement of Jericho holds a claim that is almost unimaginable. Here, around 10,000 years ago, a community of Neolithic hunter-gatherers did something unprecedented. They built a stone wall. This was not a simple fence. It was a formidable defensive barrier, a ring of stone surrounding their settlement, punctuated by a massive, freestanding stone tower rising over 8 meters high. The scale of this project for its time is nothing short of revolutionary. This was the dawn of settled life, a period before organized farming had fully taken hold. Society was small, likely organized around family groups with no formal hierarchy, no kings, and no written orders. Yet somehow, these people coordinated to quarry large stones, transport them to the site, and construct a permanent, monumental fortification. The organizational feat is the first great puzzle. How did a pre-agricultural community living hand-to-mouth muster the labor and maintain the sustained focus for such an undertaking? There was no surplus of food to feed a dedicated army of builders. Every person involved was also essential for hunting, foraging, and the daily struggle for survival. The project implies a level of social cohesion and shared purpose that we rarely attribute to such an early era. They must have had leaders or elders capable of planning and persuasion, and a communal agreement that the immense effort was worth the future security it promised. This leads directly to the second, haunting question. What was the threat so severe that it justified this colossal investment of energy and lives? The wall itself provides the answer. It was not a symbolic boundary. It was a serious military engineering work designed to withstand attack. The accompanying tower with an internal staircase served as a lookout and a strong point. The motivation was likely fear, but a very specific kind of fear. They were not defending against wild animals. This was defense against other people. The Wall of Jericho is perhaps the oldest physical evidence of organized human conflict, of one community fortifying itself against another. It marks the moment when the concept of us and them became solid enough to build in stone. The social structure required to build it may have been the very catalyst that created more complex society. To protect their homes, they had to organize like never before, assigning tasks, managing time, and deferring immediate needs for a long-term goal. In this way, the stones of Jericho are more than a wall. They are the foundational blocks of civilization itself, born not from peace, but from the grim necessity of collective defense. This early turn toward communal protection through engineering sets a pattern that would be repeated for millennia, but it also hints at a different kind of communal project, one driven not by fear, but by a shared, mysterious purpose that left no written explanation. The need for communal effort found expression in a different, more cryptic form on the windswept coast of Brittany. Here, the landscape is dotted not with a single wall, but with a silent, sprawling army of stone. The Karnak alignments are a forest of granite, over 3,000 prehistoric standing stones arranged in dense, parallel rows that stretch for kilometers across the countryside. While their purpose, whether ceremonial, astronomical, or territorial, fuels endless debate, their very existence presents a staggering puzzle of pure logistics. This was a project of Neolithic farmers, people who had only recently mastered the cultivation of the land. Yet they undertook to quarry, move, and erect thousands of granite megaliths, some weighing as much as 50 tons, placing them in eerily straight lines that march across the horizon. The first challenge was the stone itself. The local granite is brutally hard. Without metal tools, the builders likely used a technique of heating the rock with fire and then dousing it with water, causing it to fracture along natural lines. Then came the move. Each multi-ton pillar had to be transported from its quarry to its final position, sometimes over several miles of uneven, wooded terrain. The prevailing theory involves a system of wooden rollers, ropes made from plant fibers, and the coordinated muscle of hundreds of people, pulling in unison to inch the monoliths forward. But the true engineering marvel is the alignment itself. Standing at one end of the Grand Menek alignment, you look down a corridor defined by nearly 1,100 stones, arranged in 11 converging rows that run for over a kilometer. Achieving such a long, straight arrangement without modern surveying tools is a feat of geometry that boggles the mind. How did they plot these lines over such distances, across hills and valleys, ensuring the rows remained parallel? They likely used a series of sighting stakes, aligning them with distant landmarks on the horizon, or perhaps with the sun at a specific time of day, turning the entire countryside into a giant surveying diagram. The precision speaks of a society with not just brute strength, but with master planners, individuals who could visualize a pattern on the landscape and direct a workforce to make it permanent over generations. This was not a haphazard collection of stones. It was a deliberate, large-scale inscription upon the earth, a project whose scale alone was its message, a testament to a collective will so powerful it could make the very bones of the earth stand to attention. While the Karnak stones stand in silent ranks, another island holds a mystery written not in upright pillars, but in the very floor of the world. Across the islands of Malta and Gozo, the limestone bedrock is scarred by a sprawling, perplexing network known as the cartruts. These are not random cracks or erosion channels. They are precise, parallel grooves cut deep into the solid rock, forming an ancient transportation grid that covers the landscape like the ghostly imprint of a vanished railway. The engineering puzzle begins with their form. The ruts are not V-shaped but have a distinctive, consistent U-shaped profile, typically about 15 centimeters deep and spaced an average of 140 centimeters apart from center to center. This uniformity is the first clue that this was not natural wear but a designed system. They run for hundreds of meters, sometimes in straight lines, sometimes curving gracefully to follow the contour of the land. In places, they converge into complex junctions like prehistoric roundabouts, where sets of ruts merge and diverge in patterns that clearly indicate organized traffic flow. The mystery is not just their existence, but the specific mechanism that created them. What kind of vehicle or device, moving back and forth over centuries, could cut such clean, uniform channels into solid limestone? The most common theory points to sledges or carts with fixed, wooden wheels. The idea is that as these heavily laden vehicles traveled the same paths repeatedly, their wheels or runners, combined with abrasive sand and grit trapped beneath them, slowly ground the grooves deeper and deeper into the soft limestone bedrock. This theory is supported by erosion studies, which suggest the ruts were in heavy, sustained use over many centuries, but this explanation immediately raises new questions. How were the carts or sledges themselves constructed to maintain such a precise, unwavering gauge, the distance between the wheels, over such a long period of technological development? A variance of even a few centimeters would have created mismatched, wobbly ruts, yet the spacing remains remarkably consistent across the islands. This implies a standardized design, a cultural norm for vehicle construction that persisted for generations. Furthermore, the depth of the ruts suggests an immense volume of traffic, moving goods or materials on a scale that reshaped the very geology of the islands. Yet no remnants of the vehicles themselves have ever been found. Their purpose is another layer of the enigma. Were they part of an agricultural network, hauling soil or crops from fields to settlements? Were they used in the construction of Malta's magnificent megalithic temples, transporting the massive stone blocks from quarries to sacred sites? Or do they represent a more mundane but vital system for collecting and distributing precious rainwater in an arid environment? The ruts often lead to cliff edges or to now submerged coastal areas, hinting at a landscape that has changed since they were in use. They are a fossilized impression of daily life, a snapshot of relentless, routine movement so intense it left a permanent signature on the earth. They ask us to envision a society so active, so interconnected, that its most common journeys became etched in stone for eternity, a testament to the slow, grinding power of human industry. Beneath the waves off Japan's southernmost island, the ocean floor holds a secret that challenges the very definition of a ruin. The Yonaguni Monument is a sprawling complex of massive sandstone formations resting about 80 feet below the surface. From above, the shapes are startlingly geometric. There are what appear to be vast, flat terraces connected by sharp, vertical drops that look like staircases. There are straight, narrow channels that could be roads, and monolithic pillars standing apart from the main mass. Most compelling are the stark, 90-degree angles and long, perfectly straight edges that run for meters across the rock. It looks for all the world like the sunken remains of a ceremonial plaza or a stepped pyramid, now claimed by the sea. This discovery immediately ignited a fierce and enduring debate among geologists, archaeologists, and historians. The central question is deceptively simple. Is this a purely natural structure, a masterpiece of marine erosion, or is it evidence of human hands from a time when this area was dry land? The naturalist argument is powerful. The rock here is sandstone, which naturally fractures along horizontal and vertical planes as underwater currents scour it over millennia. The region is seismically active, and tectonic shifts could easily create the large, flat platforms and sharp breaks. Proponents of this view point to similar, though smaller, formations elsewhere along the coast, created by nothing more than the relentless physics of water and stone. Yet, those who see human agency point to features that feel intentionally designed. They highlight a triangular formation that looks eerily like a carved face, specific L-shaped corners that seem too precise for random fracture, and what appears to be a circular depression that could be a quarrying mark. The most famous feature is the turtle, a flat-topped platform with a distinct raised rim that looks deliberately shaped. The debate often centers on probability. Could natural processes alone produce such a dense cluster of architectural-looking forms in one location? Or does the combination of right angles, parallel lines, and tiered levels cross a threshold into the realm of intelligent design? The true engineering puzzle is not just identifying the shapes but proving their origin. The site's submerged state makes definitive analysis agonizingly difficult. Traditional archaeological methods like examining tool marks or finding associated artifacts are hampered by thick marine growth, strong currents, and the constant smoothing work of the sea. Any potential cut marks have been softened by 10,000 years of erosion. If humans did work here, they did so when sea levels were over 100 feet lower, placing its construction at the end of the last ice age, a time mainstream history does not associate with monumental stoneworking in this region. This places the Yonaguni monument in a frustrating limbo. It possesses the aesthetic of something engineered, yet it lacks the clear, undeniable fingerprints of a builder. It forces us to confront the limits of our perception. Are we seeing patterns because we are conditioned to find them in stone, or are we witnessing the ghostly outline of a lost chapter, a civilization whose works now sleep beneath the waves, their truth slowly dissolving in the salt water? The question of what lies beneath the waves is one of profound scale, but another discovery rewrites the very beginning of monumental human ambition on dry land. In the rolling hills of southeastern Turkey, a low mound known as Göbekli Tepe was long dismissed as nothing more than an ancient cemetery. Then, in the 1990s, archaeologists began to dig. What they uncovered was not a burial ground, but a ceremonial complex so staggeringly old it forces us to tear up the timeline of human history. This site dates back to around 9,600 years before the Common Era, a full 6,000 years before Stonehenge, and 7,000 years before the Great Pyramid of Giza. At this point in time, according to every textbook, humans were simple hunter-gatherers. They lived in small, nomadic bands, following herds of animals and foraging for wild plants. They had not yet invented pottery, metal tools, or writing. They had not even begun farming, yet at Göbekli Tepe, these same people built something that defies all those assumptions. They carved the world's first known megaliths. The centerpieces of the site are massive, T-shaped limestone pillars. Each one is a monolith quarried from the local bedrock, shaped, and then transported to the hilltop. The largest of these pillars stand over 5 meters tall and weigh an estimated 10 to 20 tons. They were then set into precisely carved sockets in the bedrock floor, arranged in great circular enclosures. This alone is an engineering puzzle of the highest order. How did a society without draft animals, without wheels, and without a settled, agricultural food surplus organize the labor to achieve this? The quarrying process itself required planning. Teams had to identify suitable limestone slabs in the nearby bedrock, then painstakingly separate them using stone hammers and wooden wedges. Once freed, these multi-ton slabs had to be dragged, likely on wooden sledges or rollers, up to the summit of the tell. The act of erecting them is another mystery. Without cranes, the builders likely used a combination of ropes, levers, and earthen ramps, inching each pillar upright before securing it in its stone socket. The coordination required for this is a revolution in social organization. It suggests that these hunter-gatherers were capable of complex, long-term projects that demanded the labor of hundreds of people, working together for a common, spiritual purpose over generations. This was not a society on the brink of civilization. It was one already expressing a sophisticated collective identity through monumental architecture. But the true depth of the mystery is etched onto the pillars themselves. These are not blank columns. They are decorated with an elaborate bestiary of carved reliefs. Serpents, foxes, cranes, scorpions, and wild boars parade across the stone in intricate, flowing detail. The work is precise and artistic, achieved by pecking and grinding the hard limestone with even harder pieces of flint. This reveals a technical mastery that goes beyond brute force. Shaping such detailed artwork on a surface that curves and angles requires a steady hand, a clear artistic vision, and a toolkit of specialized stone chisels and abrasives. The central pillars often feature stylized arms and hands, suggesting they represent abstract human forms, perhaps ancestors or powerful spirits watching over the rituals performed within the rings. The implication is breathtaking. Before humans learned to domesticate plants and animals, before they built permanent houses or cities, they felt a compelling need to create a permanent sacred space. They invested their greatest collective effort not in securing food or shelter, but in constructing a temple. This turns the traditional narrative of human progress on its head. It suggests that organized religion and the social cohesion it fostered may not have been a product of agriculture, but its very catalyst. The need to build and maintain Göbekli Tepe may have been what first forced hunter-gatherers to settle, to coordinate large groups, and eventually to develop the farming techniques that would support such a monumental way of life. The site was not built by a civilization. It may well have been the spark that created the very idea of civilization. After centuries of use, the people of Göbekli Tepe did something as mysterious as its construction. They deliberately buried their entire sanctuary under thousands of tons of earth, preserving it like a time capsule for modern eyes to find. They walked away from their greatest achievement, leaving behind only the silent, towering pillars, their carved animals forever frozen in a ritual dance we can only begin to imagine. The Antikythera Mechanism was not a solitary spark of genius in the ancient darkness. It hints at a much larger fire, a tradition of mechanical science that once illuminated the Hellenistic world. Across scattered historical texts, we find fleeting references to other incredible devices, described but never found. The most famous of these lost marvels is the sphere built by Archimedes. Ancient authors like Cicero wrote with awe about this bronze model of the heavens. It was said to be a working orrery, a geared instrument that could show the motions of the sun, the moon, and the 5 known planets against a backdrop of fixed stars, all powered by a hidden mechanism. The descriptions are clear. This was not a static sculpture, but a dynamic clockwork universe in miniature, a demonstration of cosmic order that reportedly left viewers speechless. The puzzle this presents is profound. We have detailed written accounts of a complex, geared machine from the 3rd century before the Common Era, yet not a single gear, not a scrap of its bronze housing, has ever been recovered from the earth. This absence is the true mystery. It forces a haunting question. If such a prestigious and celebrated object existed, commissioned by a Roman general and discussed for centuries, where did it go? Was it melted down for its valuable metal during some forgotten conflict? Or does it still lie undiscovered in an unmarked vault or a sunken shipwreck, waiting for another chance discovery like the one at Antikythera? The written record does not stop with Archimedes. Other Greek and Roman authors mention automated theaters with moving scenery, mechanical singing birds, and even devices that could predict eclipses. These are not myths, they are reports of actual inventions, often described in technical enough terms to suggest the writers had seen them function. This consistent thread of evidence points toward a startling conclusion. The Antikythera Mechanism was likely not a one-of-a-kind miracle. It was probably a product of a known craft, a school of advanced mechanical engineering that flourished in the great learning centers of Alexandria, Rhodes, and Syracuse. In these hubs of scholarship, mathematicians, astronomers, and artisans collaborated, blending abstract theory with practical metalworking skill. They possessed the knowledge of gear ratios, the ability to cast precise bronze components, and the ambition to model the cosmos itself in metal. This was a golden age of analog technology, yet with the decline of the Hellenistic world and the rise of Rome, whose engineering brilliance lay in arches, aqueducts, and roads rather than intricate clockwork, this specialized knowledge seems to have faded. The delicate art of building cosmos in a box may have been preserved only in a few precious manuscripts and in the hands of a dwindling number of master craftsmen, until even those threads were lost. The Antikythera Mechanism, then, is our lone, salvaged witness to a lost chapter of science. It is a fragment that proves the entire lost library of mechanical wonders was not just a legend. It was real, and its lonely existence on a museum shelf makes us wonder what other breathtaking devices from that school of thought are gone forever, leaving behind only echoes in old books and the enduring puzzle of their silence. While the Greeks modeled the cosmos in bronze, a Chinese scholar sought to listen to the very heartbeat of the earth itself. In the year 132 of the Common Era, during the Han Dynasty, the brilliant inventor and astronomer Zhang Heng presented the court with a device of startling ambition. He called it the Hufeng Didongyi, an instrument for measuring the seasonal winds and the movements of the earth. To the modern eye, his creation would have looked like a magnificent ceremonial urn. It was a large bronze vessel, perhaps 2 meters in diameter, adorned with 8 dragon heads spaced evenly around its top. Each dragon held a bronze ball in its mouth. Below them, crouching with upturned mouths, sat 8 corresponding bronze toads. The design was symbolic, drawing on Chinese mythology, but its intended function was brutally practical. According to historical records, this vessel could detect the direction of a distant earthquake. The principle described is deceptively simple. Inside the sealed urn, a central pendulum was suspended. When seismic waves from a far-off tremor reached the device, they would cause this pendulum to swing. Its motion would then trigger a mechanism that released just one of the 8 bronze balls from a dragon's mouth. That ball would clatter into the waiting mouth of the toad below, producing a loud sound to alert observers. Critically, the specific dragon that released its ball indicated the compass direction from which the earthquake waves had arrived. This was not a local shock detector. Court annals report an instance where a ball dropped from the west-facing dragon, yet no tremor was felt in the capital. Days later, a messenger arrived from a region hundreds of miles to the west, reporting a devastating earthquake. The device had sensed what human senses could not. The engineering mystery lies not in the concept, but in the lost internal architecture. The historical texts describe the pendulum and the dragons, but they do not detail the precise mechanism that translated a pendulum swing into a selective, directional release. How did the device ensure that only one ball was dropped, and the correct one at that? A simple, freely swinging pendulum would jostle in many directions during a quake, potentially triggering multiple releases. Zhang Heng's genius was likely in a system of levers, latches, or channels that acted as a mechanical filter. One compelling modern hypothesis suggests the urn did not contain a single pendulum, but 8, each one delicately balanced and connected to a specific dragon's release mechanism. Only the pendulum aligned with the incoming seismic wave's path would receive enough force to trip its latch. Another theory proposes an inverted pendulum, a heavy mass on a rigid rod that would tilt in one dominant direction, engaging a set of interlocking gears that channeled the motion to a single outlet. The debate among historians and engineers is a lively one. Some reconstructions show a beautifully intricate system of gears and escapements, rivaling the complexity of a clock. Others propose a simpler, more elegant solution using inclined planes and counterweights that would be more robust and easier to manufacture in the 2nd century. This is the core of the puzzle. We have a clear account of what the device did, but the blueprint for how it did it has vanished. Every modern attempt to build a working model is an educated guess, a test of one engineering philosophy against another. The true sophistication of Zhang Heng's seismoscope remains locked in that silence. It stands as a testament to an empirical understanding of geophysics, a machine that listened for the distant groans of the planet and transformed them into a clear, mechanical signal, centuries before the science of seismology even had a name. Zhang Heng's seismoscope listened for tremors in the earth, but on the open sea, another ancient tradition listened to the ocean itself. The Polynesian expansion stands as humanity's most audacious act of maritime exploration, a feat that redefines the limits of ancient engineering. Without maps, compasses, or metal tools, these navigators set out across the greatest expanse of water on the planet, the Pacific Ocean, in vessels that were masterpieces of wooden engineering. Their double-hulled canoes, or wakolua, were not simple rafts. They were designed for open ocean voyages that could last for weeks. Two narrow hulls, carved and shaped from massive tree trunks, were lashed together with miles of braided coconut fiber rope, creating a stable platform that could ride over swells rather than cutting through them. A central platform carried shelter, supplies, and families, while a single, massive crab claw sail harnessed the wind. The entire vessel was flexible, its lashings allowing it to flex with the waves, a design principle modern boat builders now recognize as incredibly seaworthy. But the canoe was just the vehicle. The true engineering marvel was the navigational system, a complex living science passed down through generations. The puzzle is not that they found islands, but that they could find them again and again, traversing thousands of miles of empty blue with a reliability that seems almost supernatural to the modern mind. They did not navigate by luck. They engineered a method of wayfinding that used the entire natural world as their instrument panel. The master navigator, or PWO, would memorize a star compass. This was not a physical object, but a mental map of the night sky, dividing the horizon into 32 houses where specific stars would rise and set. By knowing which star rose over which part of the canoe at a given time of night, they could hold a course as steady as any magnetic compass, but stars are only visible at night. During the day, the navigator turned to the ocean itself. They learned to read the swells, the deep, rolling waves generated by distant weather systems. A seasoned PWO could feel the rhythm of these primary swells through the motion of the canoe, using them as a constant directional guide. When a swell reflected off a distant, unseen island, it created a subtle interference pattern in the water, a specific bump or cross swell that could be detected miles out to sea. They watched the clouds. A stationary pile of clouds on an otherwise clear horizon often hinted at an island beneath, its landmass creating updrafts. They observed the flight patterns of birds. Certain terns and boobies would fly out from land to fish in the morning and return at dusk, their flight paths acting as living arrows pointing toward home. They even learned to detect the slight discoloration in the water from underwater reefs and the taste of the air, which could carry the scent of vegetation from downwind. This was not a collection of tricks, it was a fully integrated system, a rigorous discipline of observation and memory where every sensory clue was cross-referenced with another. The navigator would often sleep in short bursts, attuned to the feel of the waves, trusting his body to wake him if the rhythm changed. Modern researchers, attempting to decode this knowledge, have sailed with the last traditionally trained navigators. They have watched in awe as these masters, without instruments, can point to an unseen island hundreds of miles away, simply by reading the dance of the water beneath their hull. The true depth of the puzzle lies in the scale of their achievement. Using this organic technology, they discovered and settled islands scattered across a triangle of ocean, larger than the combined landmass of Europe and Asia, reaching from Hawaii to New Zealand to remote Easter Island. This was not a blind drift. It was deliberate, repeatable exploration, a testament to a form of engineering that built its tools not from metal, but from memory, perception, and an intimate, generations-deep conversation with the natural world. The Polynesian navigators read the ocean's subtle language, but the Romans spoke to the landscape in a voice of pure, commanding geometry. Their aqueducts are often remembered as graceful arches spanning valleys, but the true engineering genius is invisible. It lies in the relentless, unwavering slope of the channel itself, a gradient so precise it feels like a law of nature carved in stone. To make water flow reliably for dozens of miles, from a mountain spring to a thirsty city, the channel had to descend at a constant, gentle rate. Too steep and the water would rush through, eroding the conduit walls and arriving in a turbulent, wasteful torrent. Too flat and the water would stagnate, becoming foul and useless. The Romans typically aimed for a slope between 1 in 200 and 1 in 5,000. That means for every kilometer the aqueduct traveled, it might drop as little as 20 centimeters. A child could barely perceive that incline by eye. Yet Roman engineers maintained this exacting standard over aqueducts like the Aqua Marcia, which ran for over 90 kilometers from its source to Rome. Imagine trying to lay a pipe from one city to another, ensuring it drops only a few centimeters every 100 meters, while traversing hills, forests, and rivers. The margin for error over such a distance is virtually non-existent. A single miscalculation in the highlands would mean the water would simply stop flowing miles short of its destination. The tool that made this possible was the chorobates, a masterpiece of simple design. It was a long wooden bench, perhaps 6 meters in length, supported by legs at each end. A precise groove ran along its top, which could be filled with water. Since water always finds its level, the builders could use this liquid line as a perfect horizontal reference. They would sight along the groove to align a series of stakes across the countryside, creating a level path for the aqueduct's course. For even greater precision, a plumb line could be hung from a crossbar on the instrument. The chorobates was unaffected by the wind that could disrupt a simple plumb bob, making it reliable in the field. The real challenge came in translating this level line into a constant downhill slope. Surveyors had to calculate the desired total drop for the entire route, then break that down into manageable segments, constantly checking their work as they progressed. When the terrain dipped, they built the iconic arched supports to maintain the gradient. When it rose, they sometimes tunneled straight through hills. The Aqua Claudia included a tunnel over 3 kilometers long, dug from both ends, and the two teams met in the middle with astonishing accuracy. This was surveying and civil engineering of the highest order, executed without lasers, without transits, without even a standard unit of measurement that was consistent across the empire. They worked with local feet and paces, yet their results were globally consistent in their perfection. Recreating such a project today with only their tools would be a daunting test of patience and skill, a reminder that their greatest strength was not in moving mountains, but in persuading water to follow a meticulously calculated, obedient path across them. High on wind-swept hills across Scotland and parts of Europe, the stone ramparts of ancient forts hold a secret written in fire. These are not simple piles of rock. In places, the very stones of the walls have been transformed, melted, and fused together into a dark, glassy substance. This process is called vitrification, and it turns solid rock into something resembling volcanic obsidian or industrial slag. The effect is both beautiful and deeply puzzling. These are Iron Age structures built over 2,000 years ago by communities we think of as using basic tools and simple technologies. Yet here is evidence of a process that requires immense, sustained heat, the kind of heat associated with modern blast furnaces or foundries. How, and more importantly why, would ancient builders deliberately turn their defensive walls into glass? The engineering mystery begins with the sheer scale. At forts like Tap o' Noth in Scotland or St. Suzanne in France, sections of the ramparts, sometimes meters thick and dozens of meters long, show clear vitrification. The stones, often granite or other hard rock, have not just been blackened by soot. They have been fundamentally altered, their crystalline structure broken down by temperatures exceeding 1,100 degrees Celsius. Achieving that heat in an open environment on a windy hilltop and applying it evenly enough to fuse an entire wall section is a monumental challenge. One leading theory suggests it was intentional, a sophisticated building technique. The idea is that the builders constructed a wooden framework within the stone wall, filled it with combustible material, and then set it ablaze. The long, slow burn would heat the stones from the inside out, causing them to partially melt and weld together as they cooled. The result would be a wall of incredible strength, a single, monolithic barrier far more resistant to weathering and attack than a dry stone construction. It would be a form of primitive cement created through pyrotechnology. This theory paints a picture of masterful control, of engineers who understood the properties of their local stone and could choreograph a fire to transform it. But the practical difficulties are immense. Experiments by archaeologists attempting to recreate vitrification have shown just how finicky the process is. Building a hot enough fire is one thing, but maintaining that critical temperature for days, perhaps even weeks, to allow the heat to penetrate deep into the wall core is another. The fire must be contained and fed constantly, a logistical nightmare requiring vast amounts of fuel and careful tending. If the temperature dips too low, the stones merely crack. If it gets too high or uneven, the wall could slump and collapse. The margin for error is terrifyingly small. This leads to the competing and perhaps more visceral theory. What if the glassy walls are not a product of construction, but of destruction? Perhaps these forts were not deliberately vitrified by their builders, but were accidentally fused by catastrophic attacks. An invading army might have piled immense amounts of wood against the walls and set a colossal, siege-ending fire. The resulting inferno, fueled by the fort's own wooden structures and perhaps even stores of oil or fat, could have reached the necessary temperatures to melt the stone. In this scenario, the vitrified ramparts are not a feat of engineering, but a scar of ancient conflict, a snapshot of a fortress's final, fiery hours. This theory, however, also struggles with the evidence. In many forts, the vitrification is not haphazard. It often appears in specific, strategic parts of the wall, like gateways or the innermost ramparts, suggesting a deliberate application rather than the random pattern of a sack. Some vitrified layers are found sandwiched between normal stonework, indicating multiple building phases, not a single catastrophic event. The debate between these two ideas, construction versus destruction, remains unresolved. Each new excavation and experiment adds nuance but no definitive answer. This mystery forces us to reconsider the technological landscape of Iron Age Europe. It suggests a level of pyrotechnical knowledge, whether for building or for siege warfare, that we have not fully credited to these societies. The glassy stones stand as silent, molten questions. Were they the ultimate expression of a community's effort to make their home permanent and unassailable, a literal fusion of their will into the landscape? Or are they the tragic, unintended monument to a violence so intense it altered the very geology of the hill? In their shimmering, dark surfaces, we see not just a puzzle of heat and stone, but a reflection of the two most powerful human impulses, the drive to create something eternal and the capacity to reduce it to slag. Deep within the temple of Hathor at Dendera, a curious image is carved into the stone. In a darkened crypt, a bas-relief shows two figures holding what looks like an oversized, elongated pear. Inside this bulbous object, a snake stretches the full length, its head pointing toward a small box held by a kneeling figure. To the modern eye, it is an irresistible visual puzzle. The shape is uncannily like a light bulb filament inside a glass enclosure, connected by a cable-like cord to what could be a power source or battery. This single carving has become a cornerstone for theories suggesting the ancient Egyptians possessed, or at least imagined, electric lighting. The interpretation seems to solve other mysteries, like how the builders of the pyramids illuminated deep, windowless chambers without covering the walls in soot from torches. It is a compelling, seductive idea. Yet mainstream archaeology offers a very different and far more detailed explanation. Egyptologists point to the rich symbolic language of Egyptian art. The object is not a light bulb, they argue, but a stylized depiction of a lotus flower, a symbol of creation and rebirth. The snake emerging from it is the god Harsomptis, a manifestation of the sun god, often shown as a serpent inside a lotus, representing the sun's journey through the watery chaos of night before being reborn at dawn. The kneeling figure is the god Hare, holding a notched palm rib symbolizing millions of years, and the cable is actually a lotus stem connecting the scene to a jed pillar, a symbol of stability. The entire tableau is a well-documented mythological scene about cosmic renewal, not a technical diagram. This stark contrast in interpretation is the real puzzle here. It forces us to confront a fundamental question in understanding the ancient world. Where is the line between symbolic art and a literal representation of technology? Our modern minds are wired to see familiar objects. We look at a carving and instinctively search for analogues in our own world, a light bulb, a helicopter, a spaceship. But ancient artists were often speaking a different visual language, one where concepts, myths, and divine forces were expressed through a standardized set of symbols. A lotus was never just a flower, a snake was never just an animal. They were pieces of a complex religious and cosmological code. The Dendera relief sits at the heart of this interpretive conflict. It challenges us to resist the easy answer, to learn the grammar of the past before we attempt to read its sentences. Could it be that both interpretations contain a sliver of truth? Perhaps the artists, in depicting the miraculous rebirth of the sun as a serpent of light inside a vessel, were indeed describing a phenomenon of illumination, but through the only conceptual framework they had, the language of myth and symbol. They may have been representing not a manufactured light bulb, but the awe-inspiring experience of light itself, given form in a ritual context. The true engineering marvel at Dendera, then, may not be a lost electrical device, but the human mind's enduring capacity to express profound mysteries, whether of the cosmos or of technology, in the beautiful, ambiguous poetry of stone. But a carved light is a matter of interpretation. On the other side of the world, an ancient achievement is undeniably real, and its form is a shape so simple it becomes profoundly strange. Scattered across the river deltas of southern Costa Rica, lying in fields and near ancient village sites, are hundreds of stone spheres. They are not roughly round rocks. They are sculptures of impossible perfection, spheres carved from hard granodiorite boulders, some over 6 feet in diameter and weighing more than 16 tons. Their surfaces are unnervingly smooth, their curves so geometrically true that modern surveyors using precision tools have measured them and found deviations of less than a centimeter. This is not one or two curiosities. It is a collective phenomenon, a society that decided, for reasons we can only guess, to make the sphere its signature art form on a monumental scale. The immediate engineering puzzle is one of pure fabrication. How do you take a massive, irregular boulder and reduce it to a perfect sphere using only stone hammers and abrasives? The proposed method is a testament to staggering patience. Artisans likely began by heating the stone with fire and then rapidly cooling it with water to create surface fractures, making it easier to work. Then, using harder stone hammers, they would have pecked away at the surface, slowly knocking off protruding pieces. After the rough shape was achieved, the real refinement began. They would have moved to grinding, using slabs of sandstone or sand as an abrasive, rotating the sphere against the grinding surface, or perhaps rotating the grinding tool against the sphere. This is where the mystery deepens into a question of skill and consistency. Achieving a near-perfect sphere by hand, by feel, over months or years of work, requires an intuitive mastery of three-dimensional geometry. The artisan must constantly assess the shape from every angle, removing material evenly to maintain symmetry. To do this once is a marvel. To do it hundreds of times across spheres of vastly different sizes implies a standardized technique, a school of craftsmanship where the knowledge of how to find the sphere within the stone was passed down through generations. The time investment for each one is almost inconceivable. Some estimates suggest a single, large sphere could represent decades of dedicated labor for a team of workers. This forces the most haunting question of all. Why, what purpose could justify such an immense, focused expenditure of a community's energy and talent? The spheres were found in alignments near chiefs' residences, in groupings that might have marked astronomical sightlines, or arranged in patterns that mirrored constellations. Some researchers believe they were symbols of power and prestige, territorial markers for different clans. Others see them as cosmological models, representations of celestial bodies, or perhaps even the planet itself, a way to hold the perfect shape of the cosmos in solid, tangible form. Their very perfection may have been the point. In a world of irregular trees and flowing rivers, the creation of a flawless geometric shape was an act of asserting human order upon the chaos of nature. It was a demonstration of control, a statement that this culture could not only survive in the landscape, but could reshape its very bones into an ideal form. The spheres were not tools, not weapons, not shelters. They were expressions of an idea carved in backbreaking, generation-spanning labor. Their silent, perfect presence today asks us what we would be willing to build if our goal was not utility, but the pursuit of an abstract, beautiful truth. A sphere is a shape of pure, silent perfection, but in the high desert of New Mexico, the air itself seems to hold a persistent, imperfect note. For decades, a small percentage of residents and visitors in the town of Taos have reported hearing a low, droning hum. It is described as a distant diesel engine idling or a deep electrical buzz, a sound felt more in the bones than clearly heard by the ears. It comes and goes, often more noticeable indoors at night, and for those sensitive to it, it can become a source of profound distraction and discomfort. The source of the Taos hum has never been officially identified. Investigations have ruled out obvious industrial causes, local machinery, and even military activity. It remains one of the most famous modern acoustic mysteries. Yet some researchers, looking at the long history of human habitation in the region, have begun to ask a speculative, fascinating question. Could this be a modern echo of something much older? The surrounding landscape is a tapestry of ancient Puebloan sites, from the monumental cliff dwellings of Bandelier to the vast, planned communities of Chaco Canyon. These were cultures with a deep, sophisticated understanding of their environment, who engineered their homes and ceremonial spaces in precise alignment with celestial events and the contours of the land. What if, in shaping that landscape, they inadvertently, or perhaps intentionally, created a structure that interacts with the very physics of sound in a way that lasts for centuries? The hypothesis ventures into the realm of infrasound, frequencies below the range of human hearing. While we cannot consciously hear infrasound, our bodies can sense it as a vibration, a feeling of pressure or unease. Large-scale earthworks, specific geological formations, or even networks of subterranean chambers can, under the right wind conditions or geothermal activity, act like giant wind instruments or Helmholtz resonators, generating and amplifying these low-frequency waves. An ancient pueblo built into a certain cliff face, or a system of ceremonial kivas carved into the earth with specific dimensions, could theoretically channel and focus these vibrations across the valley. The builders would have had no concept of sound waves or hertz, but they were master observers. They would have noticed places where the wind sang a certain way, where the air felt different, where a sense of presence was palpable. These locations, rich with unseen energy, would naturally become sites for ritual, for connecting with forces greater than themselves. Over generations, they might have even enhanced these natural features, building walls to funnel the wind or excavating chambers to deepen a resonant frequency, effectively tuning the landscape. The modern hum, then, could be a ghost in the machine of the desert, a byproduct of ancient environmental engineering that we, with our sensitive modern bodies and our quiet nights, are only now beginning to faintly perceive. It is a reminder that the work of ancient engineers was not always about creating objects we can see and touch. Sometimes it was about shaping the invisible experience of a place, about weaving the environment into the fabric of spiritual life in ways that linger long after the last builder has gone. The landscape of ancient engineering is not only a gallery of triumphs, but also a classroom of instructive failures. In the sun-baked quarries of Aswan, Egypt, rests the most eloquent teacher of them all, the unfinished obelisk. This colossal shaft of red granite, still partially attached to the bedrock, offers a rare and candid snapshot of the monumental building process frozen in time. Had it been completed, it would have been the largest obelisk ever erected by the ancient Egyptians, standing an estimated 120 feet tall and weighing nearly 1,200 tons. But during its quarrying in the New Kingdom period, a fatal flaw appeared. Deep cracks snaked through the stone, rendering it useless. The workers abandoned it exactly where it lay, and there it remains, a fossilized ambition that tells us more about the how than any polished monument ever could. Its very presence reveals the first brutal step of the process. The obelisk was not cut free with saws or chisels. Instead, teams of laborers used simple, fist-sized balls of dolerite, a stone even harder than granite. Kneeling in the hot sun, they would have pounded these pounder stones directly against the granite bedrock, over and over, following a trench they had marked out around the intended obelisk. This was not a delicate operation. It was a war of attrition against the stone itself, a relentless percussion that would have echoed for months across the quarry. Each strike would pulverize a tiny grain of granite, slowly, agonizingly deepening the trench. To visualize the scale of this labor, imagine trying to carve a swimming pool out of solid concrete using only a hammer, and then multiply that effort 1,000-fold. The trench around the unfinished obelisk is clear, showing the intended shape, but the floor beneath it is still connected, demonstrating they would have undercut it last, likely inserting wooden wedges that would be soaked to expand and crack the final connection. The cracks that doomed this giant are the key to the lesson. They likely formed because of hidden tensions within the bedrock itself, a flaw invisible to the master quarrymen until their work was nearly done. This single event underscores the immense, ever-present risk of these projects. A single unseen fissure could mean years of backbreaking labor were for nothing. The investment in manpower, food, and organization was staggering, and it could all vanish with the sound of splitting stone. This obelisk, therefore, is not a monument to incompetence, but to the audacious gamble at the heart of ancient megalithic engineering. They were pushing their materials and their methods to the absolute limit, working on a scale where the margin for error was virtually non-existent. And that is what makes the successful obelisks, the ones that now stand in Rome and Istanbul and Paris, so utterly bewildering. The unfinished obelisk shows us the terrifying difficulty of the first step, simply getting the stone out of the ground in one piece. To then transport a 1,000-ton needle of granite, load it onto a barge, sail it down the Nile, and erect it perfectly vertical without it snapping under its own weight, seems to multiply the impossibility. This abandoned project forces a humbling perspective. Every flawless obelisk we see in the world today represents a victory over 1,000 potential disasters, a perfect alignment of skill, logistics, and sheer luck that this cracked stone in Aswan so poignantly lacked. It reminds us that our awe should be reserved not just for the finished product, but for the staggering confidence required to even begin. These scattered stones and silent chambers, from the perfect sphere to the humming desert, form a vast and interconnected puzzle. Stepping back from any single marvel, a pattern emerges across all 40. the same questions echo through the millennia, regardless of the culture or the continent. First, the relentless pursuit of precision, a surgical accuracy in stone and metal that mocks the supposed simplicity of ancient tools. Second, the breathtaking defiance of scale, moving mountains as if they were mere building blocks. Third, the ghostly absence of technique, the methods that vanish without a trace, leaving only the impossible product behind. And finally, the haunting presence of anomalous knowledge, ideas and devices that appear as isolated sparks in the historical darkness, with no clear lineage before or after. These are not 40 separate curiosities. They are 40 variations on a single, profound theme, the theme of lost mastery. Together, they suggest that our linear timeline of human progress, that steady upward slope from primitive to advanced, is at best an incomplete story. It seems that again and again, across the globe, societies reached pinnacles of empirical engineering, profound understandings of materials, astronomy, and physics, forged through generations of observation and trial. But this knowledge was not always written down in books or encoded in universal theories. It was often held in the hands and minds of master craftsmen, passed through apprenticeships and oral tradition, woven into the rituals of a culture. When that culture faded, when the last master died without an heir, that intricate, practical wisdom could evaporate, leaving behind only the monumental, silent proof that it once existed. The Antikythera Mechanism did not lead to a mechanical age. The self-healing Roman concrete recipe was forgotten. The method for walking the Moai was lost even to their own descendants. This is the sobering lesson. Innovation is not a guaranteed forward march. It can be a flickering flame, brilliant but fragile, easily extinguished by time, conflict, or simply the failure to pass the torch. That is why these achievements are not mere antiquities to be catalogued and admired. They are active, ongoing research puzzles. Modern engineers and scientists, armed with scanning electron microscopes, computer modeling, and advanced chemistry, are still trying to reverse engineer what these ancient builders accomplished with levers, ropes, and stone tools. In a very real sense, we are still catching up to them. We are still trying to solve problems they already solved, to learn secrets they took for granted. This reframes the entire endeavor of studying the past. It becomes less about looking down from the height of our technology and more about reaching back across a gap in understanding, trying to clasp the hands of those master engineers and asking, "How did you do this?" So we are left not with answers, but with a richer, more humbling set of questions. Which of these 40 enigmas speaks most powerfully to you? Is it the silent computer salvaged from a shipwreck, the mountain carved into a temple from the top down, or the perfect sphere that demanded a lifetime of patience? The conversation does not end here. Share your thoughts below. Tell us which mystery you find most compelling and why. In wondering together, we keep the spirit of inquiry alive, honoring these ancient puzzles not as dead ends, but as invitations to look deeper, to question more, and to remember that the human capacity for genius has always been and remains our most astonishing creation.